This section on general performance principles deals with the factors that control and determine the performance of an aeroplane throughout the different stages of its flight. We will start with the takeoff and then proceed to the climb, descent, cruise, and lastly the landing phase. This first lesson deals with the takeoff. The takeoff stage of flight is defined as being from brake release until the aircraft reaches a specified height, called a screen height. The screen height varies from 50 feet for Class B aeroplanes to 35 feet for Class A aeroplanes. As the aircraft accelerates down the runway, a speed will be reached where the pilot applies back pressure on the control column to raise the nose wheel off the ground. This procedure is called rotation, and it is initiated at an indicated airspeed, which is called VR. From rotation, the aeroplane pitch attitude will increase, and eventually the main wheels will lift off the runway. The speed at which they do so is called VLOF. After this point, the aeroplane starts its initial climb, and eventually will reach the screen height. However, a specific speed needs to be gained before the screen height. This speed is called the takeoff safety speed. There is a certain minimum value associated with this speed, which is usually based upon the aeroplane's stall speed and/or its control speed. But these will be dealt with later. In large twin-engine aircraft, the takeoff safety speed is referred to as V2. The takeoff can be divided into two parts. We call these the ground run and the airborne section. The first part, the ground run, is usually referred to as the takeoff roll required or takeoff run required, which is the distance travelled from brake release to liftoff. The second part of the takeoff, the airborne section, is usually referred to as the initial climb. This is the distance covered from liftoff until the aeroplane reaches the screen height. The combined length of the takeoff run required and the initial climb is known as the takeoff distance required. As pilots, we need to make sure that the takeoff distance required does not exceed the available distance at the aerodrome we are using. This can be achieved by checking those factors which affect the takeoff distance and ensuring that the performance achieved will enable us to take off safely within the constraints of the airfield. This may seem obvious, but there are many incidents to suggest that this important consideration is often forgotten. A long takeoff distance is considered to be poor performance, whereas a short takeoff is considered to be good performance. However, in commercial transport, the performance is not measured in terms of the takeoff distance, but rather in terms of the weight that can be carried. A good performance in terms of a commercial flight would be a takeoff with a large weight, whereas a poor performing aeroplane would only take off with a small weight. As a general rule, any effect that would cause the aeroplane performance to reduce would cause the aeroplane takeoff distance to increase and/or reduce the takeoff weight. To better understand takeoff performance, we need to fully grasp the forces acting upon an aeroplane and how these forces might change throughout the takeoff. Shown on screen is an aeroplane at rest at the brake release point. A typical 737-400 series has a maximum all-up mass of 62,800 kilograms. This mass will be accelerated from the center of gravity of the aeroplane towards the center of the Earth by gravity. The resulting downward force is called weight. The objective of the takeoff procedure is to create a sufficiently high enough force to oppose this weight and allow the aeroplane to fly. The principal force which is used to oppose weight is lift. In simple terms, to generate a lift force, we need a mass of air to pass over an aerofoil. The aerofoil in our case is the aeroplane wing. To make the air flow over the wings, the aeroplane must be pushed through air. The faster the aeroplane travels through the air, the more lift will be created. The aim at takeoff is to gain a sufficient amount of forward speed to create enough lift to help counteract the weight, and thus allow the aeroplane to fly. However, in order to move the aeroplane through the air, there must be a horizontal forward-acting force. This forward-acting force is generated by the engines and is called thrust. With a given amount of thrust, the aeroplane will accelerate and air will flow over the wing, thereby creating lift. A detailed explanation on how propeller and jet engines produce thrust is beyond the scope of this course, but nevertheless, brief explanations will be provided at appropriate times. The basic concept of the modern jet engine is that it draws in a large mass of air through its intake, accelerates it, and finally ejects it. The principle involved here is mass multiplied by acceleration produces a force. This is an adaptation of Newton's second law of motion. The greater the acceleration of the air, or the greater the mass of the air, the greater the thrust force produced. However, as the aeroplane travels faster, the velocity of the air entering the engine starts to match the velocity of the air exiting the engine. The result of this is that the air is not being accelerated as much. Thus, less thrust is produced. So, as the aeroplane speed increases, the thrust produced by the jet engine decreases. This loss of thrust with increasing forward speed is referred to as intake momentum drag. When the aeroplane reaches speeds in excess of 0.2 Mach, then the air ahead of the engine starts to compress, increasing the air density and therefore the total mass of air flowing through the engine. As a result, this helps to limit the loss of thrust caused by intake momentum drag. This thrust recovery is called ram recovery or ram effect. So initially, as speed increases, thrust will fall, but above 0.3 Mach, the thrust loss starts to reduce due to the ram effect. In the speed range used for takeoff, the jet-engined aeroplane never attains sufficient speed to gain the full ram effect. Therefore, in takeoff, as the jet aeroplane accelerates down the runway, the thrust will reduce. The propeller engine generates its thrust in a similar way. A mass of air is still accelerated rearwards, but the propeller is acting much like a wing, in that it produces lift, only this time in a forward direction. You will recall that if a mass of air were to pass over an aerofoil, then lift will be produced. In order to pass air over the propeller, so that it can generate lift, it must be turned through the air by the engine. Shown here is a propeller in cross-section. The amount of lift produced by the propeller blade and the amount of air that is displaced backwards is a function of the angle of attack. The angle of attack is the angle between the relative airflow and the chord line of the aerofoil. The greater the angle of attack, the greater the lift force, and the greater the amount of air displaced rearwards. When the aircraft is stationary, the airflow relative to the propeller is from beneath, as shown. However, as the aeroplane gains forward speed, more of the airflow comes from the front, and as a result, the angle of attack and subsequently the lift produced will decrease. So, similarly to the jet aeroplane, a propeller-driven aeroplane will experience decreasing thrust during the takeoff. There is one more force to consider. As the aeroplane accelerates down the runway, it will encounter several forms of resistance, called drag. Resistance from the air is called aerodynamic drag, and resistance from the wheels and the runway is called wheel drag. We'll deal with aerodynamic drag first. Aerodynamic drag, though, has two forms: parasite drag and induced drag. During takeoff, the only form of aerodynamic drag to concern us is parasite drag. Parasite drag is created by the impact of the aeroplane on the air. It follows then that as the aeroplane travels faster through the air, parasite drag, and thus the aerodynamic drag, increases. Therefore, during the takeoff, aerodynamic drag is increasing, as shown in this graph. Having discussed aerodynamic drag, let's now consider wheel drag. Wheel drag is basically the friction between the wheel and the runway, and is a function of their friction coefficient and the load placed on the wheel. As an example of this, press your finger lightly on the desk and push your finger forwards. You will notice a resistance to the motion of your finger. Repeat the scenario, but now press down harder. You will notice much greater resistance to the motion of your finger. This example aptly demonstrates that the greater the load on the wheels, the greater the wheel drag. Returning to the takeoff, as more lift is generated by the aeroplane accelerating down the runway, there will be less load on the wheels, and thus the wheel drag will decrease. Wheel drag will eventually reduce to zero once the aeroplane has achieved liftoff. To summarize, aerodynamic drag increases during the takeoff, whereas the wheel drag decreases during the takeoff. As illustrated on screen, the total effect of the drag on the aeroplane is that it increases with speed up to liftoff. Adding the thrust line onto the graph, you will recall that for either the prop or the jet aeroplane, it was stated that the thrust decreased during the takeoff. At the start of the takeoff, you can see that there is a large margin of thrust in excess of the total drag. This is shown by the blue area between the drag and thrust lines. This excess thrust is what is used to accelerate the aeroplane. Notice, though, that as the aeroplane gains speed during the takeoff, there is less excess thrust available, and therefore less acceleration. Next, we'll examine what determines the takeoff distance, and also what roles the four forces play in determining the takeoff distance. In order to do this, let's briefly examine the formula that is used to calculate the takeoff distance. The letter S is the displacement or distance required from rest to reach a specified speed, which is v, with a given acceleration, a. Acceleration is force divided by mass. The force is thrust minus aerodynamic drag and minus the wheel drag. Expanding the formula in this manner allows you to see how a change in one of the variables has a knock-on effect on the takeoff distance. For example, if there is a reduction in thrust, acceleration will reduce. If acceleration reduces, then the distance required to get to a specific speed increases. Although we have already mentioned how some of these variables change during the takeoff, we'll now analyze in detail all the factors that can affect the takeoff, with our principal concern being how these factors affect the takeoff distance.
The first of the factors that affect the takeoff is the effect of mass. Increasing mass has four significant effects on the takeoff, all of which can be observed in the formula for the takeoff distance. The first is that a greater amount of mass for a given applied force will reduce the acceleration that the aeroplane can achieve. Essentially, The heavier the object, the harder it is to accelerate it. This is the effect of inertia. More mass will create more inertia. If the acceleration of the aeroplane is reduced, then the distance required for it to reach a specific speed will increase. Therefore, the takeoff distance will increase. A second effect of mass is that there will be more load on the wheels, and therefore wheel drag will increase. An increase in drag will of course reduce the acceleration of the aeroplane. And once again, if the acceleration of the aeroplane is reduced, then the distance required for it to reach a specific speed will increase. Therefore, the takeoff distance will increase. The third effect is not as apparent as the rest. A heavier aircraft will require more lift in order to get airborne. To get this extra lift, the aeroplane will need to travel faster through the air. This means that the aeroplane will need to accelerate to a higher takeoff speed before it can get airborne. Getting to this higher speed will require a greater distance, and therefore the takeoff distance will increase. The fourth effect is that a higher mass will reduce the aeroplane's initial climb angle. This decreased climb angle will increase the distance required to reach the screen height as shown, and therefore will again increase the takeoff distance. The effect that the mass has on the climb will be dealt with more comprehensively in the next lesson. In summary, the effect of increasing mass has 4 detrimental effects on takeoff performance. Always ensure that the aeroplane mass is within the performance limitations. Mass calculations are dealt with more comprehensively in the Mass and Balance course as part of your theoretical knowledge training. The next factor which will affect the takeoff performance is the air density. This has 3 effects. The first effect is that a reduced density means that there is less weight of oxygen available for combustion within the engine. There is also less mass. As a result of less combustion and less mass, the thrust produced by the engine is reduced. Reduced engine thrust will reduce the acceleration force it can produce, and, as a result, the takeoff distance will be increased. The second effect of a reduced density concerns the takeoff speed. You will recall from an earlier lesson that in order to generate sufficient lift, a mass of air needs to flow over the aeroplane wing. If the air density is reduced, then that mass of air is reduced in any given volume. Thus, to generate sufficient lift, the remaining mass must flow faster over the wing. This is achieved by accelerating the aeroplane to a higher speed. To gain this higher speed, the aeroplane will have to travel a greater distance. Therefore, with a reduction in density, the takeoff distance will increase. However, a relationship between the speeds needs to be explained at this point. Dynamic pressure is the force of the flow of air over the aeroplane. You will recall that the flow of air over the wing is exactly what is required to generate lift. This dynamic pressure needs to be maintained to provide the same amount of lift. Therefore, when density falls, in order to maintain the same dynamic pressure and thus the same lift, the speed must be increased. Indicated airspeed works in exactly the same manner as lift, because it too is a function of dynamic pressure. To achieve the same indicated airspeed as the density falls, the true speed must increase. So with the scenario of reduced density in the takeoff, the aeroplane still needs to experience the same dynamic pressure to still generate the same lift and achieve the same indicated airspeed. But now the aeroplane must travel faster through the air to achieve these parameters. Thus we have a relationship in which, when the density falls, to achieve the same indicated airspeed, the true airspeed must be higher. The third effect that density has on the takeoff is that it will reduce the angle of the initial climb, and, as already mentioned, this will increase the distance to get to the screen height. Since aeroplane performance is affected by the air density, it is important to understand and anticipate what conditions lead to changes in air density and thus airplane performance. Although the full explanation is outside the scope of this course, high temperatures, high altitudes, and high humidity will all decrease the density of the air, and therefore decrease the takeoff performance. A useful statement to memorize is that high, hot, and humid conditions decrease aircraft performance. The next factor that will affect the takeoff performance is the wind. The aeroplane will always get airborne once a certain value of lift, dynamic pressure, or indicated airspeed is reached. However, if there is a headwind of 20 knots, then a stationary aeroplane will already be experiencing some dynamic pressure, some lift, and an indicated airspeed of 20 knots. In the case of a headwind, then, the aircraft is already closer to its flying speed, and need not travel as fast over the surface to achieve the necessary flow of air over the wing in order to fly. This forward speed over the surface is called the ground speed. Since the aeroplane need only accelerate to a slower speed, it follows that the aeroplane will travel less distance to reach that slower ground speed. So, a headwind will reduce the ground speed for any given indicated airspeed and consequently reduce the takeoff distance. A tailwind will increase your ground speed for any given indicated airspeed. Because to get the air to flow rearwards across the wing, the aeroplane must first match the speed of the wind and then move considerably faster than the wind in order to ensure enough lift is generated by the wing. Accelerating to this higher ground speed will increase the takeoff distance. The additional effect that wind will have is on the angle of the initial climb. Headwinds will tend to both increase the angle of initial climb and reduce the takeoff distance, whereas tailwinds will both reduce the angle of the initial climb and increase the takeoff distance. When examining the effects that winds will have on takeoff performance, it is recommended that you do not use the actual wind that is given, just in case that when you do actually get airborne, the wind changes, and thus your takeoff distance changes. The safety recommendation is that the takeoff planning is carried out assuming a worse situation than the one which is forecast. When calculating takeoff distances, it is recommended that you only assume no more than 50% of the headwind component and no less than 150% of the tailwind component. As an example, if the wind were reported to be a 10-knot headwind, only assume 50% of this, which is 5 knots. An important note is that there is no allowance for crosswinds and therefore no safety factor for crosswinds. Crosswinds present an additional complication because of the effect of the potential crossed controls, which would have to be applied when the wind tends to push the aeroplane off the centerline. These issues mean that aeroplanes are given maximum crosswind limits. Most performance graphs that calculate the takeoff distance have the 50% headwind and 150% tailwind recommendations already applied. The example shown here includes this. You will notice this recommendation because of the different slopes of the headwind and tailwind lines. Tailwinds have a greater effect on the distance than headwinds. This can also be seen on other graphs by looking at the scale of the headwinds and tailwinds rather than just looking at the slope. In Part 2 of the General Performance Principles Takeoff lesson, you learnt about some of the factors that affect the takeoff, namely the aircraft mass, the air density, and the wind. Part 3 continues with the factors that affect the takeoff, and it starts with the effect of runway slope. The next factor that can affect the takeoff performance is the slope of the runway. Slope has an impact on the takeoff distance because of its effect on how the component of weight acts along the longitudinal axis of the aeroplane. Notice here that a stationary aircraft on a level runway has its weight acting straight downwards towards the center of the Earth. However, when the aircraft is on an upslope, although the weight still acts towards the center of the Earth, there is a component of weight, shown here, which acts in the direction of drag, that is, backwards along the longitudinal axis. This will reduce the acceleration of the aeroplane and therefore increase the takeoff distance. Conversely, when the aeroplane is on a downslope, the weight component now acts in the direction of thrust. This adds to the forward force, therefore it will increase the acceleration and decrease the takeoff distance. A rough calculation to help quickly quantify the effect of slope is to assume that for every 1% slope, the takeoff distance is affected by 5%, or by a factor of 1.05. A general rule for airports within the United Kingdom, there is a restriction for up to 2% slope, and most takeoff performance calculations will account for slopes only up to 2%. If, however, the runway has a slope in excess of this, then permission will need to be given by the authority for the aerodrome to operate, and the pilot will also need to demonstrate competency in using it. The slope at some airfields, particularly around southern Europe, permit takeoff and landing in only one direction. Treat these runways with extra caution and always check that the current wind velocity will still allow a safe takeoff. You can check with the aerodrome information charts about the runway slopes, such as the one shown on screen. Most takeoff graphs assume a paved, hard surface. If the condition of the runway is not like this, then the effect on the takeoff distance needs to be understood and corrections have to be applied. A lot of small airfields have grass runways. The grass will increase the drag on the wheels. This drag will reduce the aeroplane's acceleration and, as a result, increase the takeoff distance. Most takeoffs and landings that you will encounter throughout your professional career will undoubtedly be on hard, paved runways. However, these surfaces, as well as grass surfaces, may be covered by standing water, snow, slush, or ice. These contaminants may cause significant performance loss to the extent that a safe takeoff is not possible. Standing water, snow, and slush behave in a similar manner to the effect of grass in that they create additional drag as the wheels pass through them. But they also create additional drag as the spray from these substances impinges on the aeroplane. This is known as impingement drag. The greater the thickness of these substances, the greater the impingement drag, and therefore the greater the increase in the takeoff distance. In fact, there may be so much contamination on the runway that the acceleration of the aeroplane is insufficient to safely get it airborne before the runway runs out. There is potentially an even greater effect on the aeroplane from ice, water, and slush on the runway, other than the effect of the increased drag on the wheels. These substances will dramatically reduce the friction between the wheel and the runway, acting similarly to a lubricant. Whilst this may not seem too much of an issue whilst trying to get airborne, it does present an enormous problem when trying to abandon the takeoff and bring the aeroplane to a stop before the end of the runway. Because there is very little friction between the wheel and the runway surface, the wheel cannot be retarded efficiently by the brakes. Otherwise the wheel will lock, and the wheel friction with the runway will reduce even further. This is most obvious when ice is present on the runway. There are other effects which runway contaminants can have on aeroplane performance, which include the possibility of a power unit failure due to water ingestion, directional control problems, and possible structural damage. It is therefore vital that the pilot be aware of the type of runway contamination, its depth, its extent, its effect on the braking, and of course its overall effect on the operation concerned. The recommendation by the United Kingdom CAA is that takeoff should not be attempted when the depth of water, wet snow, or slush is more than 15 millimeters. But check with the aeroplane flight manual in case it has a more severe restriction. The information on the contamination will be provided by the aerodrome and issued to the pilot through a report. These reports are either by SNOTAM or a runway state code. Use these reports and your aeroplane flight manual to best gauge the performance considerations. An important point to note is that there is a distinction between damp, wet, and contaminated runways. A runway is considered to be damp when there is moisture present on the surface which changes its color, but insufficient moisture to produce a reflective surface. A wet runway is one whose moisture level makes the runway appear reflective, but there are no areas of standing water in excess of 3 millimeters deep. A contaminated runway is one when there is more than 25% of the runway covered in a layer of moisture whose specific gravity is equivalent to a depth of 3 millimeters or more of water. The importance of runway contamination cannot be stressed enough, as many fatal accidents may have been avoided had due account been taken of the situation. The next factor that can affect the takeoff performance is contamination of the airframe. This includes the effect of airframe ice and excess water. Airframe ice will accumulate as a result of icing conditions being present at the aerodrome. These conditions could have resulted from a frost, freezing precipitation, or from a snowfall. The effect of these contaminants can be significant if they are not properly removed. The first effect that they have is to disrupt the airflow over the wing. This results in an increase in drag, but, just as importantly, a reduction in the lift force. The second effect is that the contaminants will increase the weight of the aeroplane, and therefore increase the stall speed. The combination of these effects is such that the takeoff distance required will dramatically increase. Icing conditions can also lead to the jamming of the control surfaces and blockage of important instruments. So it is vital that a proper pre-flight inspection be carried out, and then subsequently the correct method of ice removal is carried out. It is compulsory by law to ensure that all aeroplanes are free from ice and free from any contamination at the commencement of takeoff. It may seem strange, but excess water on the aeroplane can lead to the same effects that ice has. In heavy rain, research has shown that lift can be reduced by as much as 30%, and drag increased by as much as 25%. This, combined with increased aircraft weight, can create a significant performance loss, and thus takeoff in heavy rain really should be avoided. Unfortunately, this advice is too often ignored. Heavy rain is usually accompanied by other potential fatal hazards. These include decreased visibility, wind shear, and microbursts. Wind shear occurs when there is a rapid change in wind speed and direction. If this occurs when the aeroplane is at or near the ground with low forward speed, then there is a considerable chance that the aeroplane will become uncontrollable and may even stall. Takeoff, when wind shear is observed or forecast, should be avoided. A microburst is a column of air descending very rapidly at speeds of up to 250 km per hour, which, upon impact with the ground, spreads out in all directions. The descending column of air may or may not be accompanied by rain. The microburst is the single most hazardous weather phenomena to aeroplanes close to the ground, when they are either in the takeoff or landing phase of flight. The microburst was only first understood in the late 1970s and, after the crash of the Delta Airlines aeroplane that killed 137 people on August 2, 1985 at Dallas-Fort Worth, significant changes in safety procedures were put in place to reduce this hazard. There is a saying amongst pilot instructors that it is far better being down here and wishing you were up there than being up there and wishing you were down here. Time pressure, passenger pressure, and commercial pressure cannot and should never come in the way of safety. Delay the takeoff if necessary, and wait for the weather to improve. The last factor to consider that affects the takeoff is the configuration of the aeroplane in terms of the flap setting. Flaps are trailing edge devices used to increase the camber of the wing and generate more lift, thereby reducing the takeoff speed. However, the use of a lot of flap will dramatically increase drag as well. Let's take a look at how different flap angles can affect the takeoff distance. With no flap, the aircraft will accelerate and then climb to the screen height, as shown. However, with some flap selected, more lift will be generated, and the aircraft will get airborne at a slower speed. This can be by as much as 10 knots. However, with flap, a small penalty is paid by the fact that the initial climb angle is shallower. Nevertheless, the overall effect is that the takeoff distance reduces. If too much flap is used, then the wing will generate more drag than lift. The result of generating more drag than lift is that the acceleration is reduced and the takeoff distance is increased compared to the acceleration achieved on a no-flap takeoff. Too much flap would also significantly reduce the angle of the initial climb and exacerbating the effect. Because of the effect of large flap angles on the takeoff distance, most aeroplanes are restricted to certain flap settings on the takeoff. For example, the 737-400 series only has 2 flap settings for takeoff, either 5 or 15 degrees. As a simple rule, increasing the takeoff flap setting will improve your takeoff performance, but it will decrease your climb performance. Familiarize yourself with your aircraft and use the flap settings laid down by the manufacturer in the aircraft manual. This completes the lesson on takeoff performance. In this lesson, you should have learnt and understood all the components affecting the takeoff, and more importantly, what determines the takeoff performance. Learn the capabilities of your aeroplane and never attempt to exceed them. Never fall prey to time pressures, which make you cut corners. Most aeroplane accidents happen in either takeoff or landing phases of flight, so always prepare for the worst. The next lesson will deal with the performance of an aeroplane in the climb.